Hey guys, how's it going? I know it's been a while since I've done one of these videos, but figured I'd get back into it. A lot of people have been asking me to get back to doing it, so I am. One of the things I've been asked a lot about is like slope side stuff, and we did an introductory video already. So I'm probably gonna repeat a lot of that information, but I'm gonna get a lot more into some of the more details about it. So first things first, you're gonna have your slope. Right, we can assume that there's a retaining wall, right? I prefer T footings, by the way. And then you've got, your slip zone, whatever it is. And for basic, and then bedrock, right? Bedrock, you got your house, right? Back to the wonderful drawings, wonderful. And we had our 1 to 3 rule. And that is good for basic analysis, right? So we have 30 foot deep, gives you 90 feet to the end of your slope creep, like so. That's your 1 to 3 rule, that's the other video. But that only starts to give you like an idea about a slope. So I'm gonna go back to the basis of every video I've ever given you guys, and that was hire an engineer. A geotechnical engineer is going to do a lot more extensive testing. They're going to do a lot more other stuff. The very first thing they're going to do is create like a profile with the soils analysis to determine exactly what type of soils you have. Some soils are more cohesive than others. Some soils are more subject to like collapse than others. It can tell you if it's cut fill, where that fill transition is to native, right? How compact everything is. It's going to give you just a litany of information that takes all of this guesswork out, right? Analyzing the hillside, you're still gonna be looking at like plants and vegetation that have root systems in there, and you're gonna look at whether or not it's got a retaining wall down at the bottom. City halls, municipalities, cities, counties, whatever else, they've done a much better job about collecting and keeping data available. So you can see if like there's a retaining wall down at the bottom, how it was constructed. There was a great thing posted on LinkedIn actually through, I think it was the ASCE. It was the ASCE who did it. If it wasn't, then it was the Army Corps. But they had an analysis of what type of footing is best to resist some of the lateral loading that you get. And these, I'll make a different video that'll basically illustrate everything that they did, but that'll all be hearsay. But anyway, T footings, probably the best. L footing, totally necessary. L facing backward, horrible. So if you look at the city plans, that'll help give you some of the information, assuming that it's available, about what kind of resistance this wall will provide for the hillside, right? Engineers, though, they're also going to be getting in, they'll be dropping like slope inclinometers in there, and that takes months of testing, right? So it's great to grab a soil profile, but much like going and looking at a home and seeing that it's down a specific number of inches or whatnot, it only gives you a photo. It gives you a snapshot in time, right? We don't know what the existing level of the home was when it was built. So maybe it moved, maybe it didn't, based off tolerances and everything else from other videos. Same thing with slopes. If you create a soil profile, you're still just getting a snapshot in time. So engineers who conduct more extensive studies on slope sides will drop like slope inclinometers in there, and that will tell them whether or not any failure is isolated or if it's more like a regional issue. It'll tell you if it's accelerating, if it's decelerating, or if it's staying at a constant pace, if it's slope creep, or if it's got other types of potential geologic hazards that might be presented here, right? So it'd be great to say, hey, I'm gonna go in and drop these push piers to stabilize this house, and that will give you the vertical lift. But what happened a lot over in San Clemente actually is a lot of contractors came in and put in these push piers, and it had a couple of actual landslide failures immediately following. When those landslide failures happened, laterally there was a collapse, right? And granted, at least in one condition I can think of, those piers held the house up, but the soil mass was all gone, right? Completely gone. People's backyard dropped like 40 feet into a golf course, right? It was all over the news. You can look it up. It's pretty wild stuff. But those piers you can see are actually exposed and still holding up the house. Cool. If there was a soil shift further underneath though, and it dragged that pier and slid it off, and then the whole whole soil mass collapsed, then that house would have fell down and it would have been terrible. So is the goal of the project to level the house out and to preserve the house, or was it to stop the landslide, right? And that's why soils reports, or geotechnical investigations are so important for land masses like this, right? At minimum, you need to understand the basics. When you create, you do like a CPT or SPT or, split spoon, some sort of coring, whatever you do, like down, right? You need to figure out where bedrock is, you need to figure out where your slip plane is, you need to find out where your fill, that looks like out, cut, fill transition is, right? You need to find out your end counts, end blows. So your end blows is basically the number of blows it takes for the hammer to drop down to drive the sampler down X number of inches. I believe for split spoon it's like 6 inches, or for your standard SPT testing it's like 6 inches. Now you can use a DCP, which is a dynamic cone penetrometer test, much cheaper, much more mobile. Doesn't give you the soils, like the actual soils information, because you can't extract a sample, but will give you relative soil densities in such a way, at least if you use the Pagani DPM 3020 model that most people use. You can convert that using a calculation over into your end blows, which is a way that makes sense to most engineers. But that'll give you relative soil density, right? Where that cut fill transition is tells you roughly how deep you'll have to embed at minimum with helicals or whatever else. And you figure out how deep bedrock is, or refusal, or competent strata, or however you want to say that word. Okay, you need to find out how deep that is, because your caissons will need to sink that deep for sure if you're going to be using a caisson system. You're going to want a sieve analysis. You're going to want your moisture content. You're going to want your dry density. You're going to want your plasticity index. And you are going to want soil type, which you should have by then. I think I'm missing something, but you're going to want at least all of that information, and you're going to want that probably in multiple locations along this slope. Going back to what I was saying about the snapshot in time, if they drop a slope inclinometer into the hillside, again, it's going to tell you if it's accelerating, decelerating, or staying at a constant pace, whether it's isolated or global, more global issue. It's going to tell you all of this information, but those inclinometers take time, right? And time is not something a lot of people have. So especially in an emergency situation, when you're trying to prevent an imminent collapse, you might have to forego the slope inclinometer. I've learned a lot about emergency projects recently, which emergency is not always emergency until it's actually an emergency, which is kind of weird. But imminent failures they're tough cookies to crack, right? So you're gonna wanna analyze all of this information, get your soil profile, check out if you've got some sort of a lateral restraining system down at the bottom, usually like a retaining wall. Figure out if you can see what all went into building that retaining wall, what the footing looks like, the thickness, and what its resistances look like. And when you do your analysis of this entire site, right, take a look down there at the bottom if there is a retaining wall and drop like a level onto it and things like that, and see if this is tilting outward, right? See if it's tilting out. If it's bowing, that indicates a separate type of collapse. And there's different ways that you can handle this retaining wall down here versus something on top. So using that as an introduction, let's talk real quick about that retaining wall. No, we're not gonna, sorry. Using this as an introduction, let's just talk about other geological hazards. So you're gonna have all of this information, right? And that's your soil profile that the geotech's gonna call out. Probably should have decided that before I started drawing all this, but you know. So same house, same slope, same retaining wall, same bedrock. All right, so when you go through the geotechnical analysis, if the soils report is extensive enough or done properly, they're going to pull out information on like geological hazards in the area, historic landslides, historic fault zones, historic floodplains. You want to get as much history on this area as possible, and you're kind of going to know if you're getting what you pay for, well, first of all, based off of how much you pay for your soils report, which, whatever, but as far as bang for your buck, you should have at least an investigation into the historic geologic issues in the area, right? And other things that you should also have inside a soils report should include things like lateral stability or seismic zone that the repairs need to be designed for, right? Because if I drop, let's call it a push pier system with a helical tieback that goes into, that goes into my slip plane and ties it all. So that's some lateral restraint and that's some vertical lift. And we usually do a little bit of polymer to fill that void there to restore the soil support. Funny thing about those helical tiebacks, helical piles aren't designed for lateral restraining in County of LA, City of LA. Can't use it for anything lateral. Even if you do a axial helical pier, right? That does provide some degree of lateral stability, which is why helicals are a little bit better than push piers as far as overall support. But in LA, you can't take into account any of the lateral benefits that this axial helical pier would provide. And you can't use them laterally, I think, at all. And that's based off of the seismic design category, right? So it's cool that they do the void fill with the polymer in order to restore the soil support. That way you're neither strengthening nor inhibiting the seismic resilience of the structure. That usually helps mitigate a lot of issues during permitting. And that's cool, but if you're in a highly liquefiable soil, right? If you're in a high seismic zone or an area of high seismicity, and this is already under constructed in a way it doesn't have the right shear walls, doesn't have anything to actually resist the movement of land based off of whatever magnitude earthquake it's going to hit, then when this all starts shaking, you're going to have issues, right? Especially a helical pier that goes down that ties into the soil. Remember, target torque and target depth. If you hit a target torque pressure and then you shake all the soil around it and that soil breaks loose, do you still have the torque? No. So, same thing here. If there's a seismic issue in my native soil that's underneath my slip zone, which my helical pier has pulled into, then there's a bunch of shaking that happens all through this area, right? And if it loosens up the soil, or if the soil liquefies because it's a sandy soil with a high moisture content over on the coast or something like that, if that soil liquefies and turns to mush, is there going to be any lateral resistance whatsoever? Answer is no, right? And then you're supported basically on this push pier only and hoping that it doesn't fall off. Again, this repair system is argued with certain engineers. It's a valid argument. Maybe I'll do a different video on why that's an argument. And you guys can chime in with your 2 cents. I've been enjoying a lot of the feedback I've been getting in personal messages, by the way. I've been having a lot of good conversations with people about it, so maybe we'll do a video about that later. But yeah, so you have to figure out seismic design category that you're into. You have to figure out if these soils are liquefiable. You need to figure out if there's an imminent landslide already happening, right? If you're on the bluff, I looked at a project the other day that's literally, you got his house, he's got 3 feet, that's it, 3 feet. Cliff and the ocean. I'm thinking there's not a whole lot of lateral restraining we're going to be able to do on this project, right? This one's tough. So yes, we called an engineer and he's going in and giving us a lot of really, really cool options actually. I just learned about the acrylite, which is kind of like a soil glue, which will help stabilize all of the soil between the house and this bluff here, lock it all in together and kind of glue it, right? And that's supposed to help resist a lot of the abrasion of the ocean waves as they hit the bluff, which is really cool. Cool stuff that I'm just learning also. So yeah, I keep an open mind. I'm still learning. But that's another thing taken into consideration, and that's something I honestly didn't have an answer for. When you do polyurethane injection, you can reduce some of the lateral earth pressure when you inject underneath the structure, but it does still exert an earth pressure also, right? So if we were to inject here and it exerted a certain force, because that's only 3 feet away, if that was enough force, we would actually trigger a landslide or a cave-in by injecting our geopolymer. And I think we can all guess that's probably not a good thing, right? So that's why I'm talking about get a geotech involved, get a geologist involved. At minimum, those are the 2 things you definitely want to get done. Develop your soil profile, preferably do it over a period of time. Check for other geological hazards, historic landslides, historic floodplains, anything that will give you more and more and more information on whatever hillside that you're analyzing. Because the more information you have, being armed with that information, it will tell you about the local or regional issues, which will help develop the repair system that you want to apply to this particular project that you're looking at. So kind of a weird, random, different video, but yeah, I've got a couple more ideas for hillsides and discussions to have, and thank you guys for tuning in. It's been a while, and I hope to get back to doing these for a bit. Feel free to like, subscribe, whatever thingy with the buttons, and then feel free to also leave a comment, private message me, or leave it below. Love to hear some feedback. Love to hear any commentary or suggestions you might have as well. Thanks so much. Hope you guys have a good day.